My name is Conor Cunningham. I work for Microsoft on the query processor team. I'm an architect there, which means that usually whenever you find a problem in the product, you can blame me. I'm going to give a talk today on update queries and sort of how you can read how they work, and I'll explain what that means in a minute. So I obviously don't live here in England. I live in the States. I work at Microsoft, although I live in Texas, and I've been at Microsoft 10 or 15 years, building mostly database engines and query processors. I went outside the company for a little bit and did startups and consulting as well, so I have sort of a customer perspective about what it's like to work with Microsoft as opposed to just for Microsoft. I like to come to conferences like this and talk to you because I think there's a lot of great ideas happening out in the field, and it helps me when I go back to develop the next round of features to understand what you're doing with that product. And you do things that we can't imagine in Redmond, and so getting to pick your brain is actually a very, very valuable thing for me. So I love listening to your questions. I wrote a chapter for a book that you can read if you want to see more about what the sorts of things I do, the Optimizer chapter in the SQL 2008 internals book. I also have a blog where people send me questions. I'll usually post up answers so that everyone can read what the answers are to the people, people's questions to me. So in this talk, I'm going to try to do one main thing. I'm going to try to teach you how to understand the update plan generation mechanism. So all the different operators you see in update plans, how many people have looked at an update plan? Yeah, this is an interactive talk, by the way, so you better, no sleeping. How many people understand what happens in an update plan? Right? And the answer, I probably shouldn't even raise my hand, but we're going to talk today about that. So that's what this talk's going to be about. You're going to be able to look at the operators and at least get a sense for what the optimizer is generating in terms of plan shape and what query execution is doing in terms of execution. So you can understand why the optimizer picks a certain plan shape in some cases. Not all cases, but enough for you to go out and do more work on your own. So that's the goal of today's talk. I will be talking about internal components of the query processor, and that means a couple of things. One, it's the truth, but if you were to call CSS and say, Connor told me X, they'll probably laugh at you, right? This is not the documented surface area of the product. This is 1 or 2 levels below that. So while we're perfectly happy for our customers to know that, and we want you to know that because we think it will help you build better applications, be aware that we may change that from release to release if we have a good reason to do so. Okay? So here's the basic agenda for the talk. I'm going to sort of give you a primer on the way to think about update plans, and then we're going to build out different ideas from that. Do they have Halloween in England? Do you guys have Halloween here? The kids dress up and do the candy and all that? Okay, good. This is important. My daughter is very much into Halloween, and she was very disturbed when I told her there was an actual feature in our product for Halloween protection. She seemed to think that was a very bad idea. So we'll talk about plan shapes and some of the different operators and how things like foreign keys work, locking, index views, how you update views that are not indexed, and we'll talk about partitioning some. And even this is just pretty much scratching the surface of what it means to do an update plan, but it should be enough for you to kind of guess how the other parts work. So this is the overview that I would give to, say, a first-day developer working on our team, except that I've done, instead of using the debugger to look at things, I've actually just built it so you can see it from the outside. So when I say update, I actually mean inserts, updates, deletes, and merge, because internally they just have one operator called the stream update operator. Now, most of the examples I'm going to give today are actually update examples, but insert and delete are trivial modifications of update when you get down to it. So you hear update, but really it's just all of those data modification operators. Okay, let's keep going. So let's get started. Here's the first thing you need to know. When you have an update, the first thing you have to do is find the rows you want to update. Then you have to compute the new values for what you want to update, and then you have to write them. It's really that simple, right? Find the rows, compute the new value, write them. And that pattern you'll see throughout this whole talk. If you don't learn anything else today, this is a good starting point. Because if you don't learn this, the rest of it will be very, very confusing. So let's look. It may be a little difficult to see in the back. I'll post all my slides on my blog, Conor versus SQL. So don't be afraid. You don't have to write all this down quickly. Just absorb, right? We're all here to have some fun. So I'll tell you what's happening here, because really they're just generic examples anyway. So I created a table, and I inserted a row in the table. I created an index on the table, and then I set that column equal to something, just for fun. So we read. We use a seek because we have an index, and we can say, yeah, the where clause can be satisfied by the seek. The top, ignore for now. We compute the new values, and then we go and update, right? So far, so good. If you can start here and understand the system seems to be doing something that makes sense, this is the easy part of the talk. So if anyone doesn't understand this, it's okay. Tell me now, and we'll go through it in more depth, because the rest of it will get worse. Okay, good. So if you have an insert, instead of having a seek, you'd have a constant table here, which is just an in-memory representation of whatever your scalar values are. If you had a delete, we would filter, and then instead of the update, you'd have the delete operator at the end. So they all have basically the same pattern. Find the rows, compute new value if you need to, do whatever your modification operation is if you need to. Okay, let's go one level deeper. So when you look at a query plan, it's not really obvious just looking at the plan what's happening underneath the covers. Who does what and which component, where do the locks get taken. All those things are just sort of black magic voodoo. So let's talk about what the basic separation of architectural duties is in the system, and this will help you understand why certain things happen when they do, when you look at update plan shapes that we're going to see today. So if you can see here on the picture, there's a couple of different areas. The top area is where the query plan is, and that's going to be the area of query execution. So all the different operators you see in show plan are kind of up in that top part. Down below is the storage engine, and it's sort of hidden. It's the hidden partner in this endeavor. It does a couple of things for the query processor so that we don't have to have the query processor code be any more complex than it is today. Specifically, the query processor doesn't know how to deal with locks directly, and it doesn't really deal with buffering rows directly. So whenever you try to say, I want to get a row for the next row to do that seek or the filter or whatever, you're going to be going to some sort of operator in the query processor that then talks to the storage engine and says, give me a row. And it says, is the row in memory or is it locked? And you'll go up, no, I'll lock it, and then I'll load it up into the cache, put it there, and then I'll return back that row to the query processor to do whatever it wants with it. And the storage engine at that point sort of says, I don't know what you're doing. It doesn't have any real knowledge of the query plan other than one or two little things. And so that's sort of the separation. So the key piece that I want you to understand is that buffering is an implicit act as far as the query plan is concerned, and locking is sort of an implicit act as far as the query plan is concerned. Does that make sense? Okay. Let's see. I have everything. Oh, yes. One more key detail. Uniqueness. If you have a unique constraint, primary key constraint, the storage engine has the logic to implement that. So when it goes and maintains the index for us, it keeps track of how all the B trees work, including is there a duplicate key in here that shouldn't be here. So whenever you try to insert a duplicate key into a unique index, the storage engine is the one that would fail. The query processor would just say, insert it. It doesn't care. And then the storage engine would fail. So that's the separation of duties. Does that make sense? Okay, now, we've talked about things so far at a logical level. Let's delve one level deeper and understand what it means to physically do an update. Right? If you have just one table, a heap, an update is sort of conceptually possible to put in your brain and say, oh, yes, I go look at the page on disk, and maybe I modify the value, and then I write the page back out to disk. We're actually also logging it to a second location, but for the purposes of today, we'll just say we write it in place. Now, the part that gets funny is, what happens when you create that secondary non-clustered index? Well, you have to keep track of updating all of them, right? And how does the system do that? Well, it actually is trickier than you think. The system actually adds extra columns onto your tables without telling you in order to help make this possible. So otherwise, you would have one copy of the data over here in your heap or your clustered index, and you'd have another copy over in a secondary or non-clustered index, and you wouldn't really know how to link those up. Right? So you might have the value 5 in your column 1, and then you just wouldn't be able to tell if you had two 5s which one it was on each access path. Your B tree is really a secondary copy of the data, and that's really the mental picture you should have. So what you're really saying when you create 100 indexes on a table is, I want to have 100 copies of these columns, and I want you to somehow maintain them all for us. Right? So it's starting to get a little bit scary for me to think, well, how on earth are we going to keep all that straight? And the way that we do it depends on what your clustered index structure looks like. If you have a heap, then what it really is just a series of pages. And the way we keep track of rows in that is we have a bookmark, a physical locator to a page, and then an offset within that page. And that's how secondary non-clustered indexes would be able to reference that structure. So whenever you create a non-clustered index on a heap, we'll go and add this extra column to the non-clustered index. If you have a clustered index that's non-unique, then we also could have the possibility of having duplicates between our access methods, right? And we have to figure out how to resolve that. So in order to resolve duplicates in a clustered index that's non-unique, we have a special column that we have called the uniqueifier, because we're really, really good with names. And the uniqueifier is a 4-byte value we just make up when you first insert the row. And then we put it in the clustered index, and we also will put it in the secondary non-clustered index structures. And then when we try to go and figure out are these two the same, we can say, are they the same uniqueifier value? And if they are, great. Otherwise, they don't match and it's some other row. Right? And if you have a unique clustered index, do you have to do all this? This is the interactive portion. Nope, she gets it. Bonus for you. Here you go. You get a drink. Free drink for you. No, her. She got it right first. Okay, so now, how do you see what's there? Because this is making your rows wider. If you're creating these indexes, those take space. What do you do to go see that? Right? Now, this is what this example is for. You can see there's a couple of these DMVs that we created, and you can go see these extra columns that get created that shouldn't be there because they're not in your user script. We add them for you, and you can kind of go there and check. Well, they'll always be added at the end, and then you have this isUniqueifier thing on the side. So depending on which example you have, you can go see what's physically there. And that way, when you actually go look at the physical pages, you can see how we're doing the joins together. And if you don't understand this, then you won't see how we can group all these together. So this is pretty important. And you can get free drinks if you follow along in this talk. Okay, so the next thing we're going to talk about is Halloween protection. Right? So this doesn't really have anything to do with Halloween, the holiday, except that it was found on Halloween. And the basic problem goes as follows. Let's assume that I have a heap, and let's assume that I have a secondary index. And that secondary index is salary, on the salary. So you have a list of everyone's salary here. And we want to give everyone a 10% raise, which seems like a pretty good idea unless you're the boss, right? So what happened was it built a plan where it qualified the rows by seeking on the non-clustered index and scanning all the values that were less than 25,000. And for each one, it would say, oh, yes, let's go compute the new value, multiply times 1.1, and let's go write that. And the storage engine would remove the row from where it was in the B tree and put it in the new spot. And then it would go get the next row. And eventually, it would hit that first row again and then increase its salary again by another 10%. So eventually, everyone's salary was at least 25,000. Right? So that's not what we wanted. And the reason why this is happening is you're reading data that you've already touched, right? So the mechanisms that you have to be able to architect the query processor and the storage engine layers aren't able to hook up and make that work well without some solution to this. And the basic solution is phase protection, which means you read out all the things that qualify before you start trying to write anything. And in our case, you spool those. So whenever you see spools in your update plan, often it's because of this. And spools obviously are expensive, so we try really hard not to do them. But sometimes they're absolutely needed, and that's okay, because you don't want to have the Halloween problem. Okay, so let's see an example. And again, you'll be able to see all the slides. I'll talk to this. It's too hard to make it all fit otherwise. So it's the same basic example as before. We have a salary table. We have a non-clustered index on salary, and we're trying to update the salary table to multiply everyone's salary times 1.1, right? So if you go here, you can see there's a seek, a spool, compute the new values. Apparently, we need 4 compute scalars this time. I'll talk to the development team about that. And then the update. We don't really need 4 compute scalars. We're just lazy, and we haven't fixed that problem yet. Doesn't matter for performance. So the issue here, when I first created this table, I didn't have any rows in it. I tried to create this, and it actually created a different plan that just had a table scan with no spool. And I was really angry because, of course, this is a Halloween protection example, and there's no spool. So why was that? What? And therefore? Well, no, it still has to scan things because by the time we can compile the plan and cache it, and you can insert rows before the plan becomes invalid. So the actual reason is that it's faster to scan the heap when there's very little data in the table. So you have these cases where there's flip between a seek and a scan. This is exactly the same problem you see in select queries. It's just initially it's trying to read the rows, and it says, well, there's only 1 or 0 rows, so we'll just scan the heap. But as soon as you start adding enough rows, it has a tipping point where the seek plus the spool cost is cheaper than scanning the whole heap. Yes, sir, Thomas. Right, so the question is, If you are locking one row at a time, how do you prevent other people from moving the rows around? And it depends on what your isolation level is. If you have read-committed isolation, which is the default, you'll hold locks on things you're changing, and in the case of an update, you'll hold them until the end of the transaction. But rows that you haven't touched yet can move around before you get there, and that's considered okay. And if you try to have someone else go modify a row that you've touched here, then you can't, because when you go to the seek, you're getting all the rows that qualify, and you're holding locks on those for the duration of the operation until the update statement completes and the transaction commits. I'm not allowed to give you drink tokens. Okay, so now let's get to the advanced topics here to see who's really paying attention. What happens under read-committed snapshot isolation? How many people know what read-committed snapshot isolation is? Okay, does anyone know what happens of the set who's here? No? So let me explain what read-committed snapshot isolation. So read-committed snapshot is a different model where instead of reading the rows at the current time, instead you can read them at the start point of your transaction. So all the values you see would be coming out at the very, very start of the transaction. If someone else was changing them, you wouldn't see any of their changes until you try to go complete your statement, move on to the next statement, or the next transaction, depending on how it's configured. So how on earth does that work? Well, the storage engine is actually implementing that for you by versioning all changes, and it's sort of a copy-on-write model. So if someone else goes and modifies a row, it keeps track of all the active transactions and sees who's got all the data. And if someone's modifying it, then it'll keep a copy around. And then when you go read the storage engine, you say, I want to read it at this particular transaction timestamp, which was the start of the statement. So as a result, do you need to spool? You don't need a spool, but we do. And the answer is because we didn't bother fixing that, because it wasn't worth. We haven't got around to it yet. But fundamentally, you're right. You don't have to spool. It could go a little faster, 5% faster, if we didn't have that spool in there under read-committed snapshot. But we don't actually want to recompile the plan when you change your isolation level, because it's not part of the key right now. So we build a plan that works under all the isolation level modes. And so there's a trade-off there, and we haven't bothered trying to force customers over. But long-term, if our customers start using read-committed snapshot more and more, then you could imagine that becomes a better trade-off for us to go do the engineering work to invest in. So I told you there would be questions for everyone today. Okay, so let's move on to the next topic. How many people have seen what a wide update plan is? Any idea? Narrow plans, wide plans? Okay, good. See, you're learning tons of stuff today. So the optimizer can build a plan that goes and for each single row, we'll go and get the row, compute the new value, and then determine how to write that row to every single index, and then get the next row and do that, write it to every single index. If you have 10 indexes, we'll do 10 writes in order, right, per row. But after you do enough changes in a single update statement, what you're doing is actually random IOs for every single one of those, potentially, if they're not in the cache. And that can be very expensive. It might be better, instead, to convert those into sequential IOs and to perform the changes in the order of the actual index. Since all indexes are sorted, you would then sort by each index and then apply the changes in order. And that can be faster on your disks, right? So wide update plans are typically better for big batches, and they're not as good for really small plans. For small plans, you want to do that row at a time model, because the random IOs are okay. You don't have to pay the overheads of all the sorts. So you're trading off sorts versus random IO versus sequential scans. This is what we do all day. Anyone want to come work with me? Let me know. So the interesting part is that in addition to the batch issue, where there's a performance trade-off, there's also some functional issues, where some of the code paths that we have in the system actually require that you use wide update plans in order to maintain the structures, because it's just not worth implementing them through both. It's more likely that you're going to be in the batch mode, or we just didn't get around to it. So in the case of index views, for example, if you create an index view in a table, then that's going to force updates on that table to be wide. And that's interesting because that means your updates will be slower for small updates. So that might change how you design your application. If you're going to have index views as part of your strategy, you might want to make sure you're not just doing singleton updates all day. Make sense? Okay, let's do an example. So here's the narrow plan. So I created 3 indexes on the same thing because I'm lazy. And I have the same basic plan. We have the table scan, we have the 4 compute scalars, and then we have the update. No Halloween protection in this case. And if you look at the properties of that table update, you can see the objects that are being updated. Right, so this is how you can go look at SSMS and see what's happening in my plan. Is it narrow or is it wide? and then what structures are happening. So that means when you do every update to that, it's going to be potentially 4 random IOs to do the writes, not counting the log writes. Because there's 4 indexes. There's the base, well, there's the base structure and then 3 extra indexes. Make sense? Okay, let's do wide updates. Wide update plans tend to get really big, and they're very hard to show on PowerPoint, so I'll see what I can do here. I created an index view, I think. Yeah, I created an index view on the same basic table. You have a table scan, and then you have some compute scalars, and then you do the original update. So here's the read, compute, update part from the original pattern that we looked at. And then we take the output of the update and start doing stuff with it. We have the actual after image, and we do all sorts of stuff with it. So there'll be a whole bunch of different features that you can see that have that concept. Does that make sense to everyone? So the update operator will perform the change, and then it'll pass back up the new values, not the old values. So operators above that will see the after image. So if you have after triggers, they would use the after image. Make sense? Okay. So in wide update plans, we have to have this graph, essentially. And we represent the graph using really just a tree, but there's an operator that's really in 2 places. There's a table spool up there, and that table spool, we actually write into the table spool when it's being fed from below like this. And then later we come back and read from the spool again. So we take the set of all the rows that you changed against the base structure, the clustered index or the heap, and then we come back and read them to determine what to do against the index view. Right? And so the key operators you should see here are the spool in both places. So we're writing to the spool over there, reading to the spool here. We have a sequence operator up at the top. And that sequence operator says, give me all things from this child, and when you're done, then go back to this next child. So all it's doing is ordering the operations. So we want to update the clustered index first, and then update the index view. The other thing that you'll see is split sort collapse, which is how we basically get things into the order of the index. And I'll have a more detailed example of that in a few slides. How many people use index views? A couple of you? Okay. So now you can see what the plan shapes look like. Okay, so next let's talk about split sort collapse. So let's say I have a primary key on a column, just an identity, right? 1, 2, 3, 4, 5. I have a couple rows in there, and I do update table set primary key equals primary key plus 1. Now I want to go take that and move 1 row forward, and I write it into the storage engine. What'll happen? It'll error because there's a unique key there, right? So I have to do something to make that not happen. So we have to get smart and do all this work in the plan shape to be able to avoid phantom primary key and unique key violations. You guys had no idea of all the work we do for you, did you? So in order to make that work, we have these operators called split sort collapse. And what they actually do is compute the net change to the index in the order that it has to be applied to avoid these phantom key update violation errors. Let's see how that works. So if I'm updating, I've got a little example here. It's the same basic thing. I'm going to set column equals column plus 1. And on the left-hand side, you can see update 1 to 2. So it's from 2. Update 2 to 3. Update 3 to 4. Does everyone understand the basic syntax? Okay. So split converts updates into a delete plus an insert, because those are logically equivalent, right? So all we're really doing is taking the update and splitting it in 2 pieces. And then we sort based on what the operation is and what the key value is, so that we can move things around into the right order and avoid the fact that you're going to be updating things in the wrong order and hit the storage engine limitation. And then we collapse, which puts things back down into the right shape. Now, why do I update 2 to 2 and 3 to 3? That seems like a waste of time. Why would I do that? Anyone? Why? It already exists, yes. So why would I need to update a value to itself? You have to speak up. I can't. To keep it on the same page. Well, it's already on the same page. To fire the triggers, you're getting closer, but that's actually not true. The update operator itself would record that separately. Yes? To pass the changes on to any other indexes, also not true, but very good guesses. Update the other columns, no. What? You do, actually, sort of. To get them in the log, you're getting close, very close, but not quite right. In the back, you're going to have to yell. Well, yes, but in this case, I'm setting 2 to 2. There you go, to force taking out the locks, because we don't want someone else to go and change it to something else while we're in the middle of our transaction. You get a free alcoholic beverage. It's my way of making sure that no one asks too many questions, because they'll be too drunk by the end to ask any more. So yeah, this actually, when I first did this preparation, I was doing the homework for this, and I went and looked at the actual set of rows, and I was angry because I had been led to believe when I was a much younger developer that this was just collapsed down, and the collapse part actually would get rid of these duplicate cases. But it turned out that it was just not true, and I had forgotten about the locks. So don't feel bad. I didn't get this for 7 years. Okay. So now, let's move on to the next topic. How many people here have foreign keys in their schema? Ah, very popular. Anyone have any idea how they work? Well, you get to figure out now. So remember how we took the after image of the update in the earlier example, right? We were able to maintain secondary structures like index views. Well, we can also take the after image of an update, and we can use that to perform validation logic on the change that you've made. So if you have a primary key table and a foreign key table, those things have to be linked together, right? The foreign key has to reference a real primary key value. So if you update the foreign key value to something that's not legitimate, then it should error, right? Well, it's not a unique key violation, so the storage engine is not going to do it for me. So let's figure out what happens. So we qualify the rows, compute the new change, write to the clustered index, and then we have this nested loop join thing with another seek. And what are we doing? We're looking up into the primary key table to see if the after image of the row exists in the primary key table. You're allowed to change that value. It just has to point to something real on the primary key side. So we just perform a join, see is there anything real there. And if there is or isn't, then we have this assert operator, which just does a little bit of computation like a compute scalar. And if it doesn't qualify, then like in programming languages, it'll assert and throw an exception, roll back the transaction. So it won't let you make a change if you don't have a primary key that matches it up. So now you can see how that pattern can be enforced. All sorts of things you're learning today. So the other thing that I guess I should point out is that when you do insert with outputs or update with outputs, how do you think it works? We're just sending back the stream that comes out of our update operator, right? So it's the same mechanism. So that's how all those features work together. So next time you go try those, you can see, well, why is it working? It's because you're actually seeing the results of the update, and we're then just putting it in some table or table value parameter for you to use in your next statement. Okay, we've talked a little bit about locking, sort of implicitly. Let's talk about how you can go see what's happening with the lock manager based on all these operators, right? So you can go take it to the next level. So there's a couple of things you need to understand about what it means to lock. It's perfectly fine for us to build a plan and then have it lock, but that doesn't mean that you won't get deadlocks, right? In fact, it's even possible for us to deadlock inside of our own plan if we're not careful. So there's actually all sorts of heuristics that we apply to what shapes we generate in plan generation to make sure that you don't have tons and tons of deadlocks. So let's talk about an example. Let's do update table, set column equals column plus 1. And then let's have two people run that at the same time. So what happens? We read the row. We have shared locks for that, right? Then we compute the new value. So we both read 1. We both compute 1 plus 1 is 2. And then we both try to update, which will try to convert that into an exclusive lock. But neither can convert to an exclusive lock because both of them have a shared lock. So in order to get around this problem, what we actually do is the query processor tells the storage engine, don't take a shared lock, take a special kind of lock that's called basically an intent for update lock, so that it's compatible. It's called a U-lock. And you can see it's compatible with other S-locks, so other non-update queries can read, but any query that's doing another update has to block. And that way they can be done in different order, right? Because one of them won't be able to get the same U-lock as the other one, and then they'll have to wait till after. So that avoids that deadlock scenario. You guys are all experts on deadlocks, right? Yeah, so am I. Don't worry. Dizzying. So what I wanted to show you here is how you can get a little better at it. Basically, if you want to see what locks get taken in any of the examples that are here today, all you have to do is the following. Begin a manual user transaction, run the command that you want to see, and then you can go look at this DMV, sys.dmtran locks, and it'll show you the list of locks, including what they are. Unfortunately, it won't show you at every single operator, So you won't see the U lock be taken here and then the X lock be taken once it gets it to there. But you can see what's the result of those because it won't be committing the transaction. So those locks are still held until you commit the transaction because we have to block other queries from updating the same data. Sound good? So now you have something to go try when you get home. So we have some heuristics to keep track of certain update plan shapes not deadlocking with other instantiations of the same plan, but the query processor doesn't reason about the totality of all plans running in the system. So it's possible that you could have two different plans that both access resources in an order that's not the same. So you could have one accessing resource A first and then resource B, and another doing resource B and resource A, and two different query plans would just not know about each other. And those would show up as deadlocks in the profiler if you would go look at the graphs, right? And the solution is you would go hint your update plans to change the order or which index they're searching so that you can avoid those cases. And that can be a very painful trade-off because you might be hinting to a slower plan to get better concurrency. Yeah, I blew my mind the first day too. Okay, so now, for those of you still awake, let's talk about index views. Index views are this nasty, nasty beast, and they are so much fun for someone who works on database engines to build because they are the coolest thing since sliced bread. Do they say that in England? Yeah, this works okay. Okay. I get in trouble in Redmond because I have all sorts of Texas colloquialisms that I use, and I'll spit it out, and then I have colleagues from other countries, and they'll just look at me funny, and I can never tell, so I always have to double check. So anyway, if I have an index view is based on a tree definition, just like any other query that you can see, and that tree definition has some pieces which work just fine when you run the original query, but then if you go update that original base table, we have to figure out the net change to the index view, because an index view is just another table that's a result of a query that we're maintaining for you. Right? And if we don't do that work, then you do select star from the index view and it wouldn't return the same results, and you'd probably be less happy about that. So let's talk about how we do index view maintenance. Index view maintenance in terms of update plans works pretty much the same way as what we've seen in some of the other examples, except what we're doing is just far more complicated. We have to take the whole original view definition, and we have to take the original table out of the bottom where you would be doing the update. So if I have a view based on T, and I'm performing an update on T, then what I have to do is transform that view definition into, if I were to give you the change to T, can I perform the change to the index view? And all the funny restrictions that we have on index views are pretty much set up so that mathematically it will work efficiently without having to go recompute the whole thing every time, which you wouldn't like either. So we have all sorts of restrictions so that we can have efficient maintenance of index views, and this is roughly how it works. We take the original view definition. In this case, I just did a sum of column 1, group by something else, over a table, and then I want to convert that into a different operation that figures out, given a new row in T, what would I do to the index view? And then I built this nasty plan on the right-hand side that goes and figures out what's the net change to that persistent index view structure. Impossible, right? Well, I'll show you. It's actually not that hard. It just takes a little while to get your head wrapped around it. Okay, so here's another example. And for space, I cut out the first part of the wide update plan of an index view, because you remember that wide update plans are required when you have index views. So all I have is the index view maintenance part, right? So the spool, where you wrote to the spool, is sort of up there hidden and you don't see it. And then down here, we read from the spool. So far, you guys are there. It's not too hard to follow. So the thing that you would ordinarily do is you have the index view itself, the persistent structure, which is just a table. And then we have the delta, where we're actually computing different things here. So instead of running the original view definition, we go and do all this magic t-sql stuff on expressions to figure out what happens. And so you see this thing here, some case when act 1019 equals 3, then minus column 2, otherwise just column 2. What is that all about? Any ideas? No? So if I'm computing the result of a sum in the index view, the interesting part about sum is if I took a row out, I could just subtract from the sum. If I insert a new row, I can just add to the sum. So it's possible to maintain the index view by realizing that there are certain mathematical properties about the aggregates that we allow to allow them to be incrementally added and maintained. So in this case, for sum, we know that we can always just add them all together. And we don't have all the data, but we can know that adding a new one is easy and removing one is also easy. Except when you get to the last row of a group and you want to remove that. right? Because then you have to get rid of the row in the index view. So what do we do then? Well, we actually force you to have count star or count big star in your index view. So you ever seen that restriction? You have to have count big star if you have an aggregate in index view. Well, this is the reason why. You actually have to be able to understand when you get to 0, what that really means is we have to delete the row out of the index view instead of just subtracting from the sum. Make sense? Now you know why index views don't support every single operator. Our heads would explode if we tried to make all that logic work. But fundamentally, you can see here, this is where we compute the change to the count star, and this is where we compute the change to the sum. And then after you have that, it goes up and computes what the action column should be. That action column is that, should I insert, update, or delete? And I think 3 must be delete, and that's because it's in some file somewhere in the source code. We did a great job of making it very readable. Yes? Why can't you do unions in index views? Union all we could potentially do if you made each side distinct. Unions do things that are destroying information. So you could have the value come back from either side. So we'd have to go modify the union to be able to understand which side it came from and to make it not really distinct and then hide it from you. So we're not really giving you the same benefit of incremental maintenance once you have a union, because a union really is a union all plus a distinct on top of it over all the columns. And distinct by itself is not supported, right? Even regular group by, we force you to add a count star, and that basically precludes you using union, because that way you would, if you lose information, then we can't incrementally maintain the structure without doing a lot more work to go recompute both sides, and then the query plans would be very, very complicated, and I can assure you we would get them wrong. Thomas. So Thomas is asking a very good question. Thomas works on data warehousing with me, and he's asking, how do I optimize away the sort down here? Right? Because we don't actually know that the spool is sorted, even though the stream to update it might be sorted. It actually isn't sorted in the order of the index view necessarily. And that's why we have to do the sort here. But to answer your question more physically, which may or may not interest the rest of you, the sort itself, the sort property isn't derived through the table spool operator. We just don't keep track of it. It's complicated. There's internal reasons why. But essentially, all split sort collapse have this capability. In regular split sort collapse for wide update plans, we actually will figure out how to minimize the number of sorts by converting each branch of the wide update plan to be able to update more than one index if they actually had the exact same sort. So if you tried to go create a wide index example and you didn't put it on different columns, and you had the same index, you'd actually notice that we do the same thing as the narrow plan, where we actually have an update operator with multiple indexes being updated, but they're all in the same sort order for the ones in each group. And if they're in different sort orders, then we put them in different groups. Right, and even then, in this particular case, I don't actually believe that we're sorted on the same thing. So if it probably wouldn't help you in that case, no. I would assume not, because there's no physical guarantee that the storage engine would technically give back the rows in the same order, even if they happen to do so all the time. And so our property model wouldn't keep track of that. We don't make that promise because we don't test that it always stays the same. And the storage engine guys can be tricky. And if you partition it, then of course it breaks. And we don't partition the table spool today, but maybe we will in the future. And those are the kinds of things that end up being very painful to fix if you've made that assumption incorrectly. Can't touch the chest. Microphone. Okay, so everyone now is an expert on index views, right? Good. Let's keep going. So now, how many people have actually tried to update a view instead of a base table? Not necessarily indexed. Yeah? Do you guys realize how hard that is to do? Right? We have to go and decompose the view definition and figure out what table you're really changing and work that all out, and then go transform the operation you're really doing to update the table instead of the view, and then do all that other stuff that we've been talking about for the past half hour. Right? It's actually quite fun, but it's really hard. So here, if you create two tables and you create a view as a join of the two tables with some predicate, in this particular example, I added something special. How many people know what with check option is? A couple of you. Okay, I'll explain. With check option is this thing in ANSI SQL that's sort of like if you had a view over just a portion of a table, and you wanted to prevent people from being able to modify the data so that it wouldn't qualify the view anymore. So if you were in Access or whatever and you surface this and someone changed the value of some predicate in the view to be something that doesn't qualify anymore, like so if it was less than 5 and you changed it to 10, then the row would just disappear. And you don't necessarily want it to disappear for some applications. So this is sort of like a cheap check constraint, if you will. So the way that we implement that is, again, doing the same stuff we've been talking about, right? We read and qualify, except we have to do the join now because of all the logic we had to do to make the update against the view work. We compute the new value. We update the base table. You see T1, not the view, because there's no physical structure for the view. And then we have to do the join down here. In this case, we're trying to figure out, is it the case that you still qualify the view? So we have to basically run the view definition again with the change, and then see, okay, if it worked, great. Otherwise, do that assert thing again and roll back the transaction. Easy. Okay. I think we're getting close. So now, table partitioning. How many people know what table partitioning is? Yes? Okay, partitioning is this feature that helps you deal with really big tables. And what really happens underneath the covers is you have the table, the logical table that you see, and then there's actually different physical storage engine row sets, which sounds great for you until you realize that we have to go build the query plans to maintain those things, and that's actually a lot of work. But conceptually, it's not too bad. It's an extension of all the topics we've been talking about so far. In almost every single partitioning case, what you're really doing is logically adding to the set of keys. Remember when we talked back about the unifier and which things made up the keys to hook up the various structures? Well, in order to talk from one index to another that potentially is not partitioned the same way, you take the partitioning scheme and the indexing key and the unifier and or whatever else needs to go along to make that unique. And then that all has to go in each non-clustered structure so that you can do a join back from the secondary index to the primary index when you're doing all these plans for selects or updates. And keeping that all aligned and straight is pretty good, but it's actually, it's more expensive because you have to switch row sets. And switching row sets is relatively expensive in the update operator. So I'll show an example, I think, in a minute. But overall, the key properties are, if you understand that partitioning is like additional index key columns, then you have a pretty good starting point to understand any partitioning update example. It's just like the other ones, except there's additional stuff to compute where partitions are. So we'll talk about what physically is different now. Okay, so I created a partition function, and I created a partition scheme, and then I create a table on that, and I insert some values that go somewhere, right, into one of the partitions. Now let's go do an update of that, and I set the column equals the column plus 1. Remember, I'm range partitioned in this case, so I have to keep track of a couple of things. Am I still in the same partition if I do plus 1, or do I have to move to another partition? Right, so if I've got a range from negative infinity to 10, and then from 10 to 20, and then from 20 to 30, I could be crossing that 10, 20, or 30 boundary, and I might get to the point where I don't know whether or not my row should still be in the same physical storage engine row set. It's still in the same table, but it might need to move from row set partition 1 to partition 2. So how do we do that? Well, it's pretty much the same logic we had for dealing with all the other cases, like the duplicate key violation stuff. So what ends up happening is, when we compute the new value here, we read, compute, eventually update, we actually have additional logic here. And if you look at the properties of the compute scalar, you can see that there's a couple of extra things happening here. So right here, you can see range partition new. And what we're actually doing is running the partition function there. And we're determining what's the target partition ID of this row. So if it needs to go in partition 2, that's great. Afterwards, we have added to split sort collapse to figure out not just is the changes the same, but what partition IDs are they also in. So you just add that as an extra column conceptually to the split sort collapse discussion we had. And once you do that, then you can figure out, am I adding or removing from each storage engine row set? And then I can apply all those changes in the update operator. And you pass along the new partition ID to the update operator at the very end, and it knows which storage engine row set to go to based on that partition ID. And if it's the same, you're great, but it might have to switch, which can be very expensive. So we have some caching and stuff in there to make it not as expensive, but understand that that can be a challenge. Do I cache whatever I learn once so that... No, it doesn't have to talk to the metadata to do this, so I should explain. So the partition function is in metadata, but range partitioning is pretty straightforward. There's just a list of boundaries. So there's an expression service call we can make with the list of boundaries. And if you look here, we just hard code the boundaries for this particular query into the text of the compute scalar. And that way, you don't actually have to worry. Each row has to compute its target partition, but you don't have to go to the metadata for every single call. So going to the expression service could be faster, but in the terms that we're talking here, it's actually not the end of the world, right? It's a few thousand instructions in the worst case to get the new partition. And once you have that, then you know where it goes. And split sort collapse can figure out which ones go to which partition, and therefore can avoid duplicate key violations happening across the partition boundaries, as well as get things to the right partition. Okay, now there's one other shape that I'll tell you about, but I don't really have a slide for, since we have a little bit of time. The thing that we also built in 2005, but they don't show up very often, is if you have a parallel update plan, then you can also see a different plan shape where there's an apply const table get, and then the updates on the right-hand side of that. Has anyone ever seen a plan like that? Yeah, I'm sure all of you have. I've stayed up late at night. It's okay, I know. The basic issue that you have is that storage engine row sets can only have one thread updating them at a time. But when you're partitioned, you have n storage engine row sets. So potentially you could do all those in parallel if you could figure out how to get all these things to happen. So if you were doing updates that happened to be aligned with the partition boundaries such that things couldn't move across the boundaries, there is actually a plan shape where we'll go and generate a plan where we can run 4 or 8 threads and just update a bunch of partitions in parallel. I don't know if we actually pick it in 2008 onwards. I know in 2005 we did generate this plan. And I know that it did sometimes get generated in 2008 because I saw a bug where it was incorrectly generated that I had to fix. So if you see a case where there's a... In 2005, partitioning was represented differently than it is in 2008 onwards. And what would happen is we'd have a list of partitions in a constant table that we would join with the row set. And conceptually we say read partition 0, and we pass in 0 as a parameter to the row set and get back that partition. And then we read partition 1. So that join would kind of give you that list. But it turned out that blocked a couple of things. It blocked parallel scans, and it had a few issues in terms of performance. So we took that out because it didn't scale in all the cases that we wanted to use it. So now we have a different representation where when you have partition tables, right here, you actually have a whole list of partitions you're scanning inside of this. And so that operator will know, go give me that list instead of having to join to it. So there's a funny business about whether or not we can do parallel updates. Some people always ask for parallel updates, and this is actually one of the few places in the product where we actually do that. Okay, I think we are getting close to the end. Questions? Yes? So the question is, back to the Halloween protection example, why is it that read committed snapshot isolation would mean that the spool is not required? Let's go deeper on that. So the spool will be useful to kind of read up all the rows and put them in a nice place on the side, and then not have to worry about them once you start updating, right? Because you're reading from the spool. You've already written to the spool once. You're not going to keep writing to the spool, and that avoids the problem of the Halloween problem if you have that spool there. You get that part so far, yes? Okay, so now the storage engine, if it's giving you every single row that's changed is sort of copied, and you only see the row at the time that you started the transaction, then you're never going to be able to see even your own changes. So as a result, the storage engine is kind of giving you an implicit spool, but it's not spooling everything. It's only spooling things that other people are changing, or in this case, that you're changing as well. So the reason why read committed snapshot could potentially go without a spool is that technically it's doing a spool. It's just doing it in a different way and not for the whole result set. So it's essentially a different way of spooling. And the overhead of read committed snapshot is a couple of percentage points. So it's not some people don't turn it on because they really, really don't want that hit. But it's actually very useful in some sense because you get a very consistent view of the world. And if you build, some other vendors only work in this manner. And so if you have to build applications that work for multiple database products, sometimes this is a useful feature to avoid certain types of contention that can happen in database applications. Does that answer your question? Okay. Other?
When you get the query
So the question's about the missing index DMV feature. Right. How does that work? Okay. This is not specific to update plans, although you could see them on update plans. I'll talk about them. So how many people have seen the index suggestion in show plan? Right? So there's an algorithm that we run when we're compiling a query, when we're trying to figure out what index we might want to use during the plan selection process. And we kind of know we have a where clause on this and this and this. And therefore, if we had an index on this, we would be extremely happy. And so we just kind of keep track of the fact that the perfect index would be on call 1, call 3, call 5. And then we'll record that in a global structure. And then we'll keep track of the delta and cost, estimated cost, between what we think it would cost to seek against that hypothetical structure versus the plan that we actually did pick. And so it's a guess, but it's usually accurate in many ways. It's a good starting point for looking at places where your physical index design may not be perfect. It doesn't mean that it's always right, and it doesn't mean you should always create it, but what's really happening then is, as just part of the regular process of running the optimizer, it's almost free information for us to omit that, because we know what plan we actually generated for that portion of the tree. We also know that that index wasn't there. The only piece we don't know is exactly how expensive it would be to seek against that hypothetical index. But we have a costing model that's close enough that we can make a reasonable guess so that you have an estimate of what it might save. And that's pretty much how that model works. I should contrast that with other models just to make sure that everyone here has context. DTA is the other possible way that you can go and look at this. And it actually runs a whole trace and tries to find the optimal set of indexes over a set of queries. And that's a different model because it's actually seeing what's the global cost of the system for all queries if we had these extra indexes added. The logic that I just described to you about the missing index feature is really more about a guess. For this one query locally, what would we think the benefit would be? And that could be very useful if you are going into a system that's not properly physically designed. But it might also be that it'll recommend an index that would make the whole system run a little bit slower because of that extra cost of maintaining the indexes, because of all those extra random IOs whenever you're doing your update plans. So it's not smart enough to realize all of that. And those would be the differences between those two features. And those suggestions happen in update plans because other than the update operator, it's the select query, pretty much. And that's kind of why you see it there. To us, the update operators are just side-affecting operators for things that would otherwise be select queries. Does that answer your question? Okay. Other questions? What's an eager spool? Yes. Okay. We have different kinds of spools inside of SQL Server, and some of them have different performance characteristics. So we have the two main kinds are lazy spools and eager spools. So if you really wanted to pull all of the rows up once for phase separation, you typically would do that in an eager fashion, which means I want to call getRow on my child until there aren't any more rows to get. And I want to spool them all right now. It could also be in other queries that you really just want to have a cache. So if you have an expensive subquery, and you might call it with different parameters, you don't actually want to call it for all possible parameters and spool the results, but anytime you've done it, it's worth spooling it because you expect that sometimes you'll read that again. So in that case, the operator would be a lazy spool, and it would not do aggressively getting all of its children and put it into the spool. It would just do it whenever it needs to. So anytime someone from above asks for a row, it'll pull rows and spool, but it won't necessarily do that in all cases. There's actually about 5 or 6 or 7 different kinds of spools. Not all of them are distinguished here. So if you have top in a spool, we have a special optimized version of top spool. And it's for cursoring operations or paging operations. There's another spool that does index lookups better and things like that. So we have lots of different kinds of spools, and it's usually for some specific plan shape that we find interesting, where we think that we can cheat a little bit to get the performance to be faster, to make that spool cheaper than a full spool. Lazy spool would obviously be the most expensive. Yes?
I want to ask, let's say that you're doing an insert that has an identity and maybe a default. Can you say something about the sequence of event? It has to get the identity, it has a blocking, and get the
right. So what's the question has to do with insert queries with identities and what's the order in which things happen. So An insert query would have a compute the new value and then insert the value. So it doesn't have to go seek to find rows unless it's an insert select. So if we're just dealing with an insert into a table, a scalar insert, and you have an identity column on there, or a default, what happens? When you're computing the new values that go in, remember that compute scalar in the middle step, then that's where we run the various expressions to compute things that need to get written to the table. And that includes default value expressions as well as identity computation. And that'll usually happen right before the update operator. If you look at it in the plan shape, you should be able to see gen identity. When you compute identity values, there are a couple of extra things that happen. We have to actually go to the storage engine, and there's a latch to go get the next value, and that can cause some contention, especially if you have large volumes of parallel inserts. So the computation would fit into the model that we have there, the compute new values part. The issue, the conceptual leap is that when you were computing new values, we don't care if it's your values or values that you've created as part of the schema definition. So if you have gen identity for gen GUID, or you have the identity column, or if you have default values, all of those get just created as part of that computation at the compute scalar, and you should be able to see them right there. And they would conceptually happen in that middle phase, that second step in the generic pattern that I described at the beginning of the talk. Well, no, the row could still potentially, well, when you insert, rows don't get locked until they're created, right? So yes, there's two steps there. One is when I create the row, is it locked? And there's also, can I go get the next identity value? Which, those are two separate steps. One of them is using the lock manager, and one of them is actually using a latch, which is an internal synchronization structure that you have inside the code. Yes, sir. So the question is, if you have an output clause, so a merge with output clause on a merge statement, I'm sorry, where does the stream come from? Merge statements are a little funny. So let's back up and explain merge statements, because they're very hard to do in a talk like this, because they literally hurt my head. The reason why merge statements exist is that you can sometimes combine two statements into one, and that can sometimes reduce code path length. In most cases, I'd say it wouldn't matter for the vast majority of applications, but if you get into very high-end Tier 1 stuff where you're doing benchmarking, then there are cases when you need to have this in order to be competitive in the market. So sometimes when you use merge, it can be decomposed into two update statements. In fact, all cases it should be decomposable. In other cases, you can write merge, and it's no different than insert select. But to answer your question, the merge stream is still the same basic pattern as here, except it's a wide update plan, and it has what's happening. If it's an update, if the action column is a such and such, then the stream update does one thing, otherwise it does another thing. And the output from that is still the after image, and you would only be able to do merge with outputs if it was set up along the, you have to pick which branch you're going to emit, right? So there are restrictions about what you can do semantically in merge to allow that to have a single semantic. I don't have an example to show you here, so I don't think I'd be able to cook one up in a moment. But generally, there can be two different streams there, and we force you to pick one to get it to make sense. That's how we would resolve it semantically. Excuse me. Okay, in the back. Okay, for update performance, how many indexes are too many? I don't think that there's a single answer to that question, but I'll tell you the following. Every time you do random I/O, that's potentially expensive, right? So having lots and lots of indexes has a cost in terms of maintenance on your application. If you have an application that has lots and lots of selects and very few updates, you could potentially have all the indexes in the world, and you wouldn't care because you're willing to take the hit on update to get the select query performance to be faster. It could be that you have an update load that's very high and a select load that's very low. In that case, the answer would be that you would want to have as few indexes as you can get away with. And so you'll find that there's a balance, right, when you can either find the minimum set of covering indexes that gets you good enough performance, and that would be a trade-off really dependent on your application. I've been spending this week talking to some of the big Tier 1 customers here in England, and there's a lot of cases where they have to do all sorts of very fancy things to get insert performance or update performance to be fast enough in some big ETL job. And those trade-offs really involve around documenting exactly what you want to do and then making trade-offs explicitly in your logical and physical database design to get to the behavior that you want. I don't think there's a hard and fast rule. I'll give you 2 data points as examples just to try to make it easy to think about it. We have a big bug database for SQL Server. It's about 30 terabytes. Because we attach all sorts of big binary files in it. So it's very, very big and complicated. And it's also relatively slow to update it anyway, because it's just a slow program that we use. And it's big. Right? Once you get to any big software development scale, it's just very hard to get any software program to work well. So it's always slow to update, no matter what, to the point where everyone's always angry about it, but it's not going to get any better, so let's just call it good. So creating lots and lots of indexes in this case is actually not too bad. We have a SAN, it's pretty fast, and we need select queries to be really fast, because if they aren't fast, there's a big performance cliff between queries running in 5 seconds or less and 15 minutes. And without the indexes, a lot of queries run 15 minutes, and then they just take up all the resources of the system, and then no one can do anything. So there's a trade-off that we have to make there, and the trade-off we made was have a pretty good storage subsystem and create lots and lots of indexes, and accept that index update will be slow. In other cases, you have cases where you just can't do that, right? You have to really, really say, I can only deal with 1 or 2 indexes. Your average data warehouse has a fact table, and it has just the clustered index, no secondary indexes. And the reason is you're willing to pay the cost to scan that, but you don't want to pay the cost to maintain, well, you don't want to pay the cost to store non-clustered indexes on that table. It's just too expensive in terms of disk space. So you can make those trade-offs based on whatever your application is, but I wouldn't say that there's a single rule. Does that help? Okay. Yes, sir. Right, so the question is about page compression and updates and the trade-off between turning it on and what the cost is to updates. Page compression is done down in the storage engine layer, and the impact to the query processor is how many pages have to be touched. The query processor really is agnostic at some level, other than the page count, which can change where those seek, scan, flips are in some plan choices. I think that you'll find that there's an overhead of doing the updates with page compression, because obviously it has to go fix up the page before writing it back out to disk. I wouldn't say that there's any strict guidance other than what your update load is. Right? If you have a high update load, you might find the cost of doing the updates is just too expensive. And it depends, again, just on your application. So some people are perfectly willing to take that hit. And in some cases, the compression is so good that you actually save a lot of time in I/O, so it actually pays for itself. Yes, if you've got CPU headroom. But these days, CPUs are pretty good. There's a lot of cores. People have been buying bigger and bigger machines. They're all 64-bit. There's a lot of positive things there that help make applications scale, and page compression is okay. I think you'll probably see, as a general rule, we'll have more features that take CPU overhead and give you greater value for that as one of the strategic things we probably will do. So page compression will be an example of that feature, because the cost of doing backups is just so insane. When you get to these really big databases, you have to have compression, or else it's just ludicrous. So I think that my time is up, so what I'll do is, if anyone wants to stay and ask me questions, that's great. If people would like to go now, socially, you will not offend me. I appreciate you coming. What I will do is I will answer questions right outside the door so that they can set up for the next talk, okay? Thank you very much for coming.